Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Hello to everybody who's taking a look at this recording that's under the sound of my voice. Welcome to the tutorial today on sound waves. Okay, which is the follow on from last week's session. Obviously doing wave, sound, and light. This is the sound section, and we're going to make this easy, as painless as possible. Because sound is something that we are all accustomed to. No one here is deaf, everybody here has ears, so we hear sounds. At the moment you are hearing the sound of my voice. Alright? You're hearing that at the moment. Okay. Now, the definition formally though, sound waves result from vibrations in the medium. Okay, now medium is the specific object that the sound waves obviously being generated from. Okay, at the moment, my voice, I'm the medium, or my vocal cords, or whatever, that the sound is coming from me at the moment. And that move in the direction that the sound propagates. Alright, propagates where it's heading, where it's going to. Okay. A sound wave causes regular vibrations in the pressure of the medium. Alright, and a sound wave, the type of wave that it is a longitudinal wave. It's not a transverse wave. Okay, it's a longitudinal wave in which the particles of a medium, they move backwards and forwards in a direction, and it's parallel to that direction that the sound wave travels. Okay, now the best way to study how sound waves are obviously generated, of course, would be to look at a speaker. Alright, now a speaker, alright, no matter how big, no matter how small, of course, generates a sound. And we'll find a lot of speakers at different parties. Alright, obviously that's how we hear sound, or music plays through. Mostly used for music, and also used for obviously on the microphone, if you, at a conference, TED talk, in school assembly, of course, etc., etc. Okay, but let's maybe have a little bit of a look-see or squizzle of how it look, or how it works rather. Okay, so let's title that how it works. Awesome. Okay, so a speaker has something called a diaphragm. Okay, now when a diaphragm of a speaker, it moves forward. Okay, so let's summarize that maybe. Speaker diaphragm, okay, moves forward. Especially on those speakers that got a lot of bass, you can see the speakers vibrating or whatever. All right, it moves forward. What does it do? It pushes molecules. All right, it pushes molecules of air closer together. Pushes them closer together. Okay, and that would be known as a region of high pressure, or known as compression. Okay, now when it moves backwards, okay, I'm going to summarize and say when it now moves backwards, all right, now obviously it makes space for air molecules. Okay, it makes space for air molecules, and the molecules move further apart. Okay, and then that obviously forms the area of low pressure, which is also known as let me spell it right, rarefaction. No, spelling it wrong. Rarefaction, there we go. Now when the diaphragm of a speaker now moves backwards and forwards, okay, so the backwards plus forwards movements, okay, that backward and forwards movement, alright, okay, what happens next is that it vibrates, okay, it vibrates, and therefore, the mathematical therefore, we have a sound wave that is generated. Alright, Particles moving backwards and forwards, right? That diaphragm moves backwards and forwards, and then that just pushes out those particles, and then you got a longitudinal sound wave. And that's how it works. Now, the speed of sound, all right, is dependent on the type of medium that it is propagated, or the type of medium that it passes through. Okay, now the stronger the forces of attraction or pulls between the particles of a medium, or the more rigid the material, rigid means sturdy, I think, or solid, such as steel, the faster the waves will travel through the medium. All right. Sound travels faster in ice than in liquid, and faster in liquid water than in air. All right. So if we have a look at that, so the speed of sound, so we'll use V there from mechanics, V of sound in a solid, like ice or steel, is greater than the velocity or speed of sound in liquid. Wow, in liquid, and which is greater than the speed of sound in air, so gas. Okay, so sound will travel faster in ice than in liquid, and the sound will travel faster in liquid or liquid water than in air. All right, will travel much faster. Okay, now the greater also the density, this is something I could just mention in passing, is that the greater the density or mass of the medium, all right, the slower the sound will obviously travel through it. All right, for example, a sound wave travels more slowly through a more massive slinking than in a less massive slinking. All right, and more slower or slowly in air than through a gas such as helium. All right. I think helium is a bit of a lighter gas than air. That's why it makes your voice turn very funny. And that's why it also makes balloons float. Like, very high into the atmosphere. Before eventually the pressure gets too much at the top of the atmosphere. And then, boof, it eventually does pop, burst. Now, I don't know if there's any musicians in the class, but I know I am one. Any singers? Or whatever, anybody that does anything to do with music, we always talk about pitch, all right? There's a movie called Pitch Perfect, all right? 1, 2, and 3, okay? Pitch Perfect. So pitch is associated with sound, of course. So what is pitch? What does it define? What do we use this word to define, okay? It definitely refers to how high or how low a sound is. Okay. Now the human ear, okay, our ears, what it does is the human ear perceives pitch as frequency. Okay? As frequency. Now we have a certain frequency that we can obviously hear by only, that we can only hear up to a certain frequency. Okay? For practical purposes, we can determine pitch by determining, of course, the frequency of the sound. Okay, for practical purposes, of course, we can do that. Okay, but pitch, the word pitch, when it comes to sound, is associated or refers to how high or how low a sound is. Okay, it's not to be confused with this next term I'm about to throw. Okay, which is called loudness. Okay. Let's just make this board look a bit more neater. There we go. Loudness. Usually we'd associate it with pitch after hearing or looking at that definition. But loudness of a sound is our ear perception. Okay? It's our ear's perception of the intensity of the sound. Alright? The human ear is more sensitive to some frequencies than other. Okay, the human ear will be sensitive maybe more to louder sounds, or like for example, if someone uses a loudspeaker, we'd hear that instantaneously as opposed to someone whispering. Okay, so loudness depends on both amplitude, all right, of a sound, both the amplitude of a sound wave, all right, which means that the greater the amplitude, the greater the energy transfer, and frequency of sound. Okay, whether the sound is at the frequency where the ear is either more sensitive or less sensitive. Okay, I think the human ear, we can only hear frequencies of up to 20,000 hertz. Okay, which is 20 kilohertz, and this is of course the human ear. Anything beyond that, we cannot hear. You know, we can't hear sounds that are greater than 20,000 kilohertz. We can't. And believe it or not, the sounds, remember, there's something that you might, that we are going to learn as we move on to electromagnetic radiation. Shorter wavelength means higher frequency, longer wavelengths have a lower frequency. Okay, so if we take, for example, creatures, animals such as the bat. All right, I love bats. Bats, I think bats are amazing creatures within themselves. I mean, don't like them too much though. I don't know. I think I might like a pet bat, but I mean, how do you keep a pet bat? To be honest, they hang from ceilings upside down, and I don't know. That's, you know, how do you keep a pet bat? Anyway, but I love bats. But they can hear very, very soft sounds. But those soft sounds are high frequencies. All right, they can hear for example, a spider spinning its web. We can't hear the sound that makes. We can see a spider spin a web, but we can't hear the sound. All right, it doesn't. We can't hear that. Bats can hear that. Bats can hear very, very, very movements that from small creatures, insects, whatever, frogs or whatever the heck they eat, you know, that kind of stuff. We can't. All right, we can't hear those. Okay, so that moves into the section which is known as ultrasound. All right. Ultrasound. Now, ultrasound, I just want to talk on or touch on, all right, because we're definitely going to go through it and touch on it now in that exam paper of 2017, okay, and we'll get through that in just a second. But ultrasound waves is basically sounds, the term given to sound with a frequency beyond a human ear's audible range. So in other words, it's greater than our limit, which is 20,000 hertz or 20 kilohertz. Okay, now bats, I mentioned bats, but another creature is called dolphins. They also navigate and they use ultrasound with frequencies in the range of 20 to 100 kilohertz or 100,000 hertz. All right. Ultrasound, though, is also used by humans, though, by us as people, but we use them in the medical field. All right, we use them with medical applications, okay, such as the device that's used to hear the heartbeat of a baby while a baby is still inside his or her mother's womb. All right, just for example, it's just about example of where ultrasound is used. Okay, it's used to basically. Sorry, let me just finish this. It's used to basically bounce off something and return a sound back, in a nutshell. Okay, what you want to do is you want to go through the section of wave, sound, and light, and we want to just have a look at it from an examinal perspective. We'll go through this one. This question just has some ultrasound, and this has some wave phenomenon in here as well. And the next question I think would be the next section, or the following section, from called electromagnetic radiation, but we haven't got to there yet, as a lot of students are finishing up with exams and whatever, so we'll take time to get to electromagnetic radiation before term 4 actually begins in October. So we'll just have a look at these 2 questions, maybe pull up maybe another 2 questions from another paper, and then we'll wrap up waves and sound. Okay, so this is question 6. Okay, 2 girls standing in opposite ends of a rope. They each make a pulse of the same speed. The pulse A with the amplitude of 4 centimeters. Pulse A, sorry, with the amplitude of 4 centimeters moves to the right, and pulse B with the amplitude of -6, because it's at the bottom. All right, because it's at the bottom. -6 moves to the left. The pulses meet at point C, which is a little middle dot right there. And 6.1, we won't go. I'm going to go through the questions with everybody, and then I'll give you one to do on your own. So it may be in another paper, but let's do this paper together. State the phenomenon observed when 2 pulses meet at the same point. I don't know if anybody remembers this from last week, but this is called, let me just title the paper first. So let's do grade 10. This is the common paper, 2017, paper 1, and 6.1, it's called the superposition of pulses. Okay, let me just read the question again. This one, yes. Okay, state. Okay, so it's got 3 marks. Okay, so we got to explain a little bit. Okay, so it's called the superposition of pulses. Basically, this is where we take the algebraic sum of the amplitudes of the 2 pulses that occupy the same space, at the same time. Okay, so those are 3 marks. If they just ask you to name it, that usually is for 1 mark, of course, but I mean you had 3 marks, so you had to say a little bit more, which is explain it basically. I was looking for in the question if they said name and state. State. This is actually a very good little exam and test tip. If they say state, the mark allocation will match that word. So state means to name and elaborate further, explain and give a little bit more. If they just said name, then you would just have to mention the name. Okay, you just have to mention the name. Okay. So, superposition of pulses for number 1, 3 marks. 6.2, draw a labeled diagram to show the resultant pulse when the 2 pulses meet at point C. Label the pulses clearly. Well, for 6.2, before we go ahead and draw that, let's take the algebraic. So, point C is going to obviously be the sum of A plus B. And we know A was 4 centimeters, okay, plus B was -6. So that ends up being 4 minus 6, and therefore the amplitude at point C is going to be -2 centimeters. Okay, that's just the algebraic sum, right? So we'll draw it. Okay, that's coming from that side. Okay, and pulse A, I'll draw like that. Okay, so this is pulse A. Pulse B was a little longer, so I'm going to dot it out a little bit. Okay, and then the other one I'm going to draw in maybe like another color. So this one's I'm going to draw it in a solid line. There we go. Okay, and that's pulse C, and that is obviously, so this one's pulse B at the bottom, it's pulse C, and this is obviously -2 centimeters. So as a result of these 2 bad boys meeting in the middle, we get this little one here. Obviously your one will be a bit more accurate than mine. Mine's very hard to obviously construct for now. Our 6.3's question was name the type of interference that takes place when the pulses meet. So now they just say name, so name 1 mark. Alright, so 6.3, sorry, let's keep it back in the original maroonish color. 6.3. That when obviously the amplitude of the middle pulse, or where the point where the pulses meet, is not either in a positive number, or it's not bigger than either, or it's not a positive number, or it's not bigger than either any one of the 2 pulses, then we basically got destructive interference, as that number is obviously smaller. All right, destructive interference. So don't just write destructive, write the full term, destructive interference. 6.4, I think, was determine the resultant didn't we just do that? Oh, yeah. So I think I did 6.4, sorry, in 6.2, which was determine the resultant amplitude. Sorry, I'll just did in 6.2. My bad. So we'll go back there. So this is how we obviously determine, I'll just put in brackets here, this is 6.4. 6.4. Oops. Okay, but that's obviously how we determine the amplitude, by using algebra, of course. Okay, that's exactly how we do it. Okay, I just used, instead of saying amplitude equals, I just said C, which is obviously the middle point there, equals A plus B. Do it up, C is the amplitude. There you go, you got it. All right, cool. So we already did that. 6.5, the last one here, 1 mark. How will the amplitude of pulse A be affected? After passing C, write down increases, decreases, or remain the same. Usually when this happens, all right. For 6.5, I'll leave it in white and I'll write in maroon maybe. After the 2 pulses have passed the meeting point, they usually return to their original amplitude. So the answer to this would be none other than remain or remains the same. Okay, so it will go back to its amplitude it started with, which was 4 centimeters. All right, let's do question 7 quickly. Question 7 says dolphins communicate through emission of reception of sounds. Okay, a young dolphin was separated from his mother and started whistling with a frequency of 130 kilohertz, which is 130,000 hertz. To call her, the speed of sound in seawater is much different from the speed of sound in air. The speed of sound in air, roughly in the subject, is given at about 330 to 340, but mostly 340 meters per second. But the speed of sound in water is 1,480 meters per second. Well, in seawater, to be exact in this question. Now, explain the term ultrasound, okay? Teachable moment here, 7.1. Ultrasound is basically sound with frequencies. Okay, sounds with frequencies that are higher than, oh, not that. There we go. Than what is audible. To the human ear. Okay. 7.2 was the next question there. Calculate the wavelength of the young dolphin's whistle. Alright. So when it comes to wavelength, which we learned under transverse waves, okay, we use the formula V is equal to the frequency times lambda. Now, velocity, or the speed of sound in air, we already have is 1,418. And we try to calculate the wavelength. We know the frequency, which was given at 130 kilohertz. We have to use frequency that is measured in hertz, so we have to say 130,000 times lambda. Okay, and we obviously need to divide both sides by 130,000. And on this side of here, therefore, lambda will be equal to about 0.011 meters, which is a very, very, very short or small wavelength. Alright, I don't think my pen nib will be able to even draw it remotely accurately. Okay, very, very, very short. Very, very short wavelength. Okay, so that's the wavelength of this little young dolphin. Okay, let's have a look at 7.3. Another dolphin hears the distress call of the young dolphin 2 seconds later. Okay, how far apart are the two dolphins from each other? Very nice question, this question. Okay, so the formula that we should remember from mechanics is that speed, I'll write out the word formula first, is equal to distance over time. You should remember that from mechanics. Okay, so V is equal to D divided by T. Okay, so the speed of sound in seawater is 1,480. That's equal to the distance, which we're not sure of, so we'll leave that as little d. And the time was 2 seconds, so multiply both sides by 2. And then we'll get an answer though of the distance, so therefore d, or distance, is going to be equal to 2,960 meters. That's how far apart the two dolphins are in this question, according to the theory. Okay. And the last question, I think, I might be wrong. Yeah, no, second last question, 7.4. They say the speed of sound in air, there's the number that I mentioned earlier, is 340 meters per second. Briefly explain why the speed of sound in air is different to the speed of sound in seawater. Okay, well, we start off by saying, you don't have to write the bullet points down, but I'm just going to kind of speed up my little answer here, is that the speed of sound in air, is slower. Alright, reason why is air is less dense than water. Okay, remember I mentioned that the more dense a medium is, the faster sound will travel through it. Okay, it's less dense. Alright, in other words, particles are further apart. Right. Okay, but of course, speed of sound in seawater is faster. Alright, it is faster. Alright, because water is more dense, or we can use one word, is denser. Right, water is denser, alright, which means that the particles are closer together. Alright, so that's a good answer right there, explaining why the speed of sound in air is slower than in water. Alright, it's because, mostly to summarize, the particles, of course, are further apart in air than what they are in water. Okay, so it comes down to the density. 7.5 says, describe how dolphins use echolocation to hunt their prey. So this is now obviously explaining the whole ultrasound thing. Okay, well, first of all, dolphins send out a frequency. Okay, they send out a certain frequency. That's the one. Okay, the sound reflects off the prey of their breakfast, lunch, or dinner, and then it will return to the dolphin. Okay, it will return to the dolphin. Okay, what happens is that the dolphin will now estimate. Alright, it will estimate the distance it is from its prey. Okay, and the way it does that is it does that by using time for the echolocation to return, or for the echo to return. Okay, so sends out a frequency, reflects off the prey, it'll estimate how far or distance it needs to travel to get there, of course, by the time it took. Okay, so sometimes it might even be like, you know what, that fish is like too far. I'm not traveling from Fishhook to Muizenberg to go catch a fish. I'm just going to chill here or go look for it somewhere else, or find fish that's a bit closer to where I, of course, want to go and hunt or eat. But that's how they do it. So question 6 here for the 2018 paper. Am I correct? Wow. Yes, 2018 November paper. Here we got, say, study the two transverse waves, P and Q, as shown below, and they give you the legend or the key. P is the solid line, or the solid wave graph, and Q is the dotted one, which is slightly lower. We've got the position in millimeters, and time in seconds. Okay, so this amplitude is measured in millimeters. They said write down one difference and one similarity between waves P and Q. Okay, so this was the previous paper. Let's exit that. Okay, cool. So I think this is still 6.1. Yes. Well, one similarity is, I'll just similarity between the two is, of course, they are both transverse. Okay, they're transverse waves. Okay. Other options include, of course, wavelength. They both have the same wavelength on the graph. They both start and end at the same place. Okay, wavelength. Another similarity could be period. Start and end at the same second. So if the period is the same, then surely they should have the same frequency. Okay. Differences. Obvious one there from looking at the graph. The amplitude. The amplitudes are different. Okay, so yeah, see, same period, same start, so same period, therefore same frequency, same wavelength for both. Literally, there we go, for both trough to trough. Amplitudes are only different. Okay, P's has an amplitude, wave P has an amplitude of 15 millimeters, while wave Q only has an amplitude of 10. Now, 6.2 says for wave pattern P, write down 2 points that are out of phase and the amplitude of the wave. So 6.2.1, 2 points that are out of phase. 6.2.1. Let's look at these. Let's look at it. Definitely A and B is out of phase because A is a peak and B is a trough. A and D are out of phase, as well as B and C, so any one of those. So I'm going to go ahead and say A and D. But also A and B were out of phase, B and C was also out of phase, but I'm going to go ahead and say A and D. And the easiest one, 15 millimeters or 6.2, is just the amplitude of the wave. We just read it off the graph. Easy as pie. Now they asked for 6.3 though, define the term frequency of waves in words. Well, 6.3 frequency is basically the number of waves. Okay, the number of waves or wave pulses, but I'm going to say just waves passing a point per second. Alright, number of waves passing a point per second. Okay, period will be how many. Okay, speaking of that, I think they ask us to calculate the frequency. It's 6.4.1 for wave pattern Q, which is the dotted line. Okay, so wave pattern Q is calculate the frequency of the wave. So let's go to another layer here. 6.4.1. Okay, we know that we have the period, we know the time in seconds, so we're going to say frequency is equal to 1 over t. So we see the period of the wavelength for wave Q, for one wavelength to complete, is 1.5. So 3 seconds, 2 waves have passed already. So from here, start all the way back here, that's 1.5. So it's definitely equal to 1 over 1.5, and therefore the frequency is equal to 0.67 hertz. Okay, 0.67 hertz. 6.4.2, calculate the speed of the wave. Okay, well, speed of the wave, we definitely know that formula. Okay, V is equal to F times lambda. Okay, we've already calculated the frequency, so that's 0.67. Okay, and the wavelength, just have a look at the wavelength here, is 100 millimeters. They gave it to us from B to D. It's 100 millimeters. That's the wavelength. Okay, so from crest to crest or trough to trough, that's the wavelength there. So in meters, 100 millimeters, divide that by 1,000. So it'll be, there's 100 centimeters in 1 meter, 1,000 millimeters in one meter. So 100 divided by 1,000 will be 0.1. So I'll say 0.1. Okay, and that is an answer of 0.067 meters per second. Question 7 says, experiments were done to investigate the effect of temperature on the speed of sound. Okay, bit of an investigative question, this one. One person beat a drum while another person who was standing 50 meters away from the sound source recorded the time traveled by the sound. Okay. They performed an experiment at different temperatures to determine at different times of the day. They recorded their findings. So first temperature 0, and then the maximum temperature I see there was 25, and then of course time in seconds. And we definitely see like there's a bit of a decrease in time happening there. So they start off, and they're 50 meters apart. Yes. So they start off by saying, for the investigation, write down an investigative question. For the experiment of temperature and versus time, and seeing what that has on the effect of the speed of sound. Okay. Well, for question 7.1, okay, another question would be, good question, simple question, 7.1, that I would ask if I was doing this investigation: how will the temperature affect the speed of sound? Right, done. Okay, that's a good investigative question. And an investigative question doesn't have to be I wouldn't say well thought of. It obviously must relate to your experiment. But investigative question is basically just a question to get the investigation started in terms of what do we want to measure. All right, what are we aiming to find out or achieve from this investigation? Okay, 7.1.2. This is 1.1. Says the independent variable, and 7.1.3 would be the dependent variable. Okay, well, the independent variable is definitely temperature. Okay, temperature is independent of anything. All right, it really is. There's no factor in the experiment that's going to affect it. It's independent. It's going to increase, okay, as the day goes along. Okay, even if it's a cold winter's day, it's still going to increase. That's just how temperature works. But the dependent variable is definitely going to be time. Not time on its own, but time taken for the sound to travel. Why? Because the time, not time in terms of minutes and seconds on its own, standalone time, but the time taken for the sound to travel 50 meters. How long that takes, that is dependent on what? Well, the temperature. As what we are trying to investigate. So time taken for the sound to travel, that's the dependent variable. Don't confuse that with standalone time, because standalone time is an independent variable. Right? Standalone time, in other words, time moving along, that is independent. Okay, another dependent variable would also be the speed of sound. Okay. Let's move on. This is my last layer. I'm going to need to probably add a new layer. Okay, anyway, let's start here with this one. Okay, 7.2. Calculate the speed of sound at 20 degrees Celsius. So it's 20 degrees Celsius. We got the time there, which is 0.146 seconds. Let's see. And it's at 50 meters. Well, let's use an equation found in mechanics. Okay, let's take delta x over delta t. Okay, so let's take 50 meters, and the time was 0.146. Okay, or you could have said speed is equal to d over t, distance over time. And that'll give you about 342.47 meters per second, which is just slightly more than the normal speed of sound that is usually in air that's usually given, which is 340 meters per second. Okay, almost done. Got 7.3 to go. Write down the conclusion for the investigation. Okay, well, we can clearly see that as the temperature increases, we can see that the time it takes to travel decreases. Okay, so we can see that if the time is decreasing as the temperature is increasing, that means that the speed of sound is increasing. So the speed of sound increases. All right, that's a good conclusion. The speed of sound increases as the temperature increases. Another way that you could have said that is the time taken for the sound to travel decreases as the temperature increases, which is straight from that little table there. Okay. Okay, we could have said that the time taken for the sound to travel decreases as temperature increases. 7.4, the last question. The person who beat the drum noticed the sound reflected back after a while. Name the term used to describe the reflection of sound waves. This one's pretty easy. Echo. Okay. When sound waves reflect back and you hear the same sound, it's an echo. Okay, that's how simple these questions are. And grade 10s, that's where we're going to leave things for this tutorial on waves and sound, because we haven't done wave, sound, and light yet. We haven't done the light section, all right? That will be in the next tutorial. Thank you so much for joining me in this one. Please don't forget to like and comment on this video, as well as subscribe to our channel. Good, better, best online videos. And we'll catch you in the next one.